All right, let's take a look at the warm-up this morning. So the warm-up gives us a matrix A and a vector B, and we have three tasks here. One, to find the inverse matrix, if it exists. Two, once we find it, to kind of verify it by seeing if A times A inverse gives us identity. And lastly, to use the inverse to solve the matrix equation. So we'll start off by trying to find the inverse. So to find the inverse here, I'm going to write my matrix A augmented with the identity matrix, in this case a 3 by 3 identity. I'm going to try to row reduce it so that the left-hand side of that augmented matrix is identity. So my first operation is going to be replace R3 with R3 minus R1. Top row will stay the same, second row will stay the same. We'll get 1 minus 1 is 0, 0 minus 2 is negative 2, 1 minus 0 is 1, 0 minus 1 is negative 1, 0 and 1. What's my next row operation going to be?
R3 plus 2R2.
All right, R3 equals R3 plus 2R2. Absolutely, so I can get rid of that negative 2. I'll have 0 here. I'll have 1 here. Negative 1. Then I'll have 0 plus 2 times 1 is 2. And I'll have a 1 here. And my last step, what's my last row operation?
Going to be R1 minus 2R2.
R1 minus 2R2, absolutely. I've already finished the forward stage. I start to go backwards. It works out pretty nice. I really don't have to go backwards in that third column here because there are R0s directly above that pivot position. So I'll go to the second pivot position and I work my way back up to eliminate values above it. So I have a 1 here. This turns into a 0, 0, 1. In this position I have 0 minus 2 times 1 should be minus 2 and a 0. All right, any questions so far? So I've taken A, I've row reduced it to identity, and when I do that, this right-hand side should be my inverse matrix. Now for the test. Now I have my matrix A. I'm going to take that matrix times my inverse. Oops. 1, negative 2, 0, 0, 1, 0, negative 1, 2, 1. The result here, I'll get 1 plus 2 times 0 plus negative 1 times 0. Now in this position, I'll have 1 times, so for this position here, I'm going to take this first column times the second row. 1 times 0 plus 0 times 1 plus negative 1 times 0, so that's going to be zeros. I'll start working with the second column. This first position I'll get negative 2 plus 2 plus 0. And I will get 1 and negative 2 plus 0 plus 2. And I'll work with the third column. I'll get 0, 0, and 1. Now, looks like this simplifies to the identity matrix. Questions so far? All right, so if you didn't get through that part in the warm-up, that's hard to listen to, right? I mean, most of the time I'm doing that matrix multiplication, I'm kind of going through that in my head and mentally taking this column, rotating it over here, and kind of going through it. That's hard for me just to talk to, so if you haven't gotten to that step, it's not that valuable. It's really for me to kind of talk through that. Right? So the value for the warm-up is getting here a little bit early, so you can try to work through that and see, oh, we got a different value in the second row, second column, and you kind of double check that work or ask about that position specifically. All right, so we've calculated the inverse. Now we're going to use the inverse. Since we have AX equals B, and there is an inverse, X should just equal A inverse times B. that's what we're going to do. We're going to take our inverse matrix, 1, negative 2, 0, 0, 1, 0, negative 1, 2, 1, and multiply that by our b value, which is 3, 1, 2. This should give us our solution x. Here we're going to get 3 minus 2 plus 0, 0 plus 1 plus 0, and negative 3 plus 2 plus 2. 1, 1, and 1. That matches what I have on my notes here, so either I did it wrong twice, or I didn't make any mistakes this morning. Any questions? Anybody confirm that answer? What we got? All right, questions from the warm-up. All right, so you can kind of see that so far linear algebra is a weird mix. Very mechanical stuff like this that is just kind of a long, tedious process that we have to just mechanically go through. And there's also the conceptual stuff that we're going to go through in a little bit. So it's really a blend of both. All right, our plan for today. Finish up 2.3. When does there exist this matrix inverse matrix? We're also going to do some cleanup stuff in there, some other comments I want to kind of make, and kind of to talk about exam 1 and also some weird little things to be careful with on your calculator or on Mathematica. After that, we're going to get into exam prep. So hopefully you got through most of that exam prep, if not all of it. We'll get into little groups if you want and kind of work through the rest of it and make sure we're happy, don't have any questions. With about 15 minutes or so in class, I'm going to pass out the key. So you can kind of check through that, see if you have any questions, and that'll be it. So let's finish up 2.3 here. So we've calculated this thing. Some of this will be a little bit of repeat at the end of class yesterday. I'll talk about when there is an inverse. So for example, we're given a matrix equation like this. I have a matrix. I have a b value. I want to find x. One way to do that is to find the inverse matrix and do x equals a inverse times b. But that's only if there exists that inverse matrix. So this matrix equation, we can also think of it as a transformation. In this specific case, we'd be transforming from R3 to where? We're taking elements from R3 and mapping them to where?
R3.
R3, absolutely. All right, we're taking x values, which are three-dimensional, and we're mapping them to b values, which are also three-dimensional in this case. Okay? So we're mapping from one space to another space. We're taking this x value, we're mapping it over here to this b value. And if there's an inverse, the inverse is our multiplication by a. If there's an inverse, the inverse will take it the other direction. It will map some b over to some x. So for this inverse idea to make sense, for a inverse to exist, there must be a solution to ax equals b for every b in Rm. There has to be an x that maps to the b for all the b's. What's another way to say that? What property is that? Onto, absolutely. So it has to be onto. There can't be an extra b hanging out here. It doesn't have an x that's mapping to it. Because if there was, I mean, we can just calculate this a inverse thing if it exists, and then we take a inverse and apply it to b, and it should map us somewhere. And it should map us to the x. So if there is no x that maps to this b, there can't be an inverse thing that maps b back to x. As So we need it to be onto. We also need, there must be at most one solution to AX equals B. That A inverse operation should bring us back to the place we started from. It shouldn't be confusing. It shouldn't potentially map us back to two different X's. So what property is that? 1 to 1. So like we talked about last time, this transformation must be 1 to 1 and onto. We kind of related that back to the idea of functions. Must be. So there exists an inverse when it's 1 to 1 and onto. All those other implications kind of stem from that. Visually, we said that there's a pivot position for every row, then A is onto. There's a pivot position for every column, then A is 1 to 1. Right, there's no free variables, so there's at most one solution. So if our transformation is 1 to 1 on and onto, if we take A and row reduce it, what should it row reduce to? What should the row reduced form of A look like? Absolutely, it has to have one pivot position for every row and every column. So it looks something like identity. Now, last time we just kind of showed the giant list here. 2.3 is really about all the different relationships that come from this statement. We know there exists an inverse matrix if it's representing a transformation that's 1 to 1 and onto. That's like the easiest way to state the basic requirement here. But we know that if the transformation is 1 to 1, it implies like 10 other things. And if it's onto, it applies another 10 other things. Right? So when we lump all that stuff together, we get the giant matrix inverse theorem. It says if we have a square matrix, first of all, because it has to be square, then the following statements are all equivalent. One implies all the rest. If one is true, they're all true. So if A is invertible, then all these other things are true. A must be row equivalent to the identity matrix. Well, we just kind of talked about that, right? We can row reduce. We can row reduce to identity. The next one says A has n pivot positions. How can we justify that one's true? Why does that one make sense? Does it make sense? If A is invertible, it has to have n pivot positions. Why? We know A is an n by n. And if it's invertible, it has to be 1 to 1 and onto. So it has to have a pivot position for every row and every column. How many rows are there? N. So it's got to have at least n pivot positions. All right, the equation AX equals 0 has only the trivial solution. That's the next statement they give us. Does this one make sense?
Has that one solution.
Absolutely. Has only the trivial solution. It has a solution for sure. There does exist a solution. That means it's onto. And there's only one solution. That means it's 1 to 1. So it's just a restatement of the fact that it's 1 to 1 and onto. The columns of A are linearly independent. That's just a fancy way of saying it's 1 to 1. This is the same thing as saying it's 1 to 1. The linear transformation is 1 to 1. Well, that one's really just a statement of being 1 to 1. The equation AX equals B has at least one solution for each B and R M. Well, that's just saying that it's this is just essentially the definition of onto. The columns of A span That's another just definition of onto. And then they're saying, really, no, it's onto. And once again, all just saying the same thing over and over again. What about the next two? There exists some matrix such that CA equals identity, or there exists some other matrix D. Turns out C and D would have to be the same. But this is really just the definition of inverse. If there is an inverse, then, yep, there is an inverse. And the last one saying that the transpose is invertible. So the matrix is invertible, its transpose is also invertible. All right, any questions about all these different restatements? All right, just kind of talk from the practice exam. It's not that I'm going to say, okay, list all of these, right? It's not like you're going to have all these memorized where you have to just list 10 different things. But I might say, you know, is this true? Is this one true? Is this one true? I might phrase these as true and false, in which case you should be able to justify them. You shouldn't have to memorize them all, but you should be able to look at a statement like this and justify it with your knowledge of one-to-one and onto and the inverse and whatnot. Okay. That's really all the stuff I have about 2.3. Before I get into questions, there's one kind of warning I want to give. The first warning is about row reductions. So many of you probably already encountered this or heard it in another class as well. But a couple of homeworks ago, we had some problems where we were taking matrices that looked like this. Let me just... Oops. Something looks like this. They would say, that's an augmented matrix. I'll make that a little bigger so you guys can actually see it. And they said, you know, are there solutions to this thing? And it turns out that depending on the value of h, there are solutions or there are not solutions. Now, if you looked at the row reduced for Mathematica or your calculator, we get something that looks like this. If I look at that row reduced form, should there be solutions to this system?
No.
There shouldn't be. But if you row reduce by hand, you got a different result. In fact, if you row reduce by hand, you got something weird that looks like this thing. Okay. Now, why? Why would you get that? Well, essentially when Mathematica or your calculators or any other program does that row reduction, it gets to this step along the way, and then says, okay, I want to turn this into a 1. So I'm going to divide by this thing to turn it into a 1. Now, anytime we divide by something where there's a parameter in there, a little red flag goes off, our math spider sense should go off and say, wait a second, I'm dividing by something, I better make sure I'm not dividing by 0. And so I have to say, well, when is this 0? And anything I do past that division does not apply when this thing is 0. Well, for some reason, the calculators and Mathematica, they don't kick out that warning. You have to be very careful about how you state the problem to account for that situation. Okay? So be careful. If you're row reducing a parameter, basically you can't trust your calculator. Now, of course, in Mathematica, they have a way for you to turn that thing off. You know, if you do 0 test, exclamation point 3q, blah, 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 right, which none of us are going to know. So bottom line is, if there's a parameter on that right-hand side, you have to be careful. Right? You have to do the row reduction by hand. And so be aware for that. There's a question in the exam. You have to recognize that and not just trust your calculator value. We have to know how to use the calculators and when we can use them and when we can't use them. Okay? Any questions about that? Okay. Then my only other statement is about a specific question on the practice exam that there was an error on. Question number 9. I was talking about the effects of multiplication by a matrix A. I wrote A to be 1, 1, 0, 0. And had you describe the action. It would kind of be confusing to describe that action. You probably could, but could be doing a couple things there and it's just weird. I meant to have the matrix 1, 0, 0, negative 1. That's what I really wanted us to work on. So you could still discuss whether the first one was 1-to-1 onto both or neither, but it would be harder to describe the actual action. So replace that matrix with this one to answer that question. Right, so use this matrix instead, because we should be able to look at that matrix and describe what it's doing as a transformation. Because we can think about its action on E1 and E2. Okay, so make that adjustment. And other than that, that is all the talking I'm going to do. And so what I'd like you to do is finish up those practice exams. We'll probably go until 8:40, and then I'm going to kind of do a walkthrough and make sure we have completion on this. So that way I know that you've worked on it before you came to class. You have answers down. I'm not going to check them for correctness or anything. But as long as it's complete, you'll get credit for this quiz assignment. And so I'll check for completion then, and then I'll also pass out the keys. So you have about 10 minutes to look through the keys and see if you have any questions about the keys. And that will be it. I want you to treat this as maybe a sample exam kind of thing, not a all-inclusive study guide. So there definitely could be questions not on this that could be on the exam. There's not a whole lot about inverse matrices on this one. So you can anticipate like a question like the warm-up would be fair game, even though that kind of question is not on here. So once again, this isn't all-inclusive. It's just a good starting point. All right, so go ahead. Like I said, I encourage you to get in groups, compare answers. Is a good way to start maybe, see what everybody got. Feel free to ask questions. I'll be walking around as well to answer questions.